Imagine standing 625 meters above a canyon floor. That's taller than any skyscraper in the entire country. You're on the Huajiang Bridge in southwestern China. But here's what separates this bridge from every other bridge on Earth. Engineers didn't just build across impossible terrain. They split a mountain in half first. You're about to see how 22,000 tons of steel, that's 3 times heavier than the Eiffel Tower, were suspended 625 meters in the air using a cable crane system that doesn't exist anywhere on the planet. Before this bridge existed, traveling from one side of Huajiang Canyon to the other meant 2 hours driving winding roads through mountains. Now it takes 2 minutes. That's not just convenience. That's an entire region being pulled out of isolation. There's a saying in Guizhou province where this bridge sits, "No 3 feet of flat land." It's not poetic, it's literal. More than 90% of this region is mountains and hills. The landscape is stunning, often compared to the Swiss Alps, but it made development almost impossible. Historically, this province was isolated. Getting there was difficult. Moving through it was torture. The Chinese government saw opportunity. Starting in the late 1990s, they began massive infrastructure projects: airports, high-speed rail, expressways. Today, Guizhou hosts 32,000 bridges, a staggering number, but most are unremarkable. This one, it became a world record, and not by accident. Before engineers could even begin construction, they had to decide cable-stayed design or suspension. Cable-stayed systems use tall towers with cables running directly down to the deck. It looks impressive, but for extreme spans, it has limitations. They chose a steel truss suspension bridge, technology proven in rocky, mountainous environments worldwide. The cables anchored directly into bedrock, providing stability that nothing else can match. But before construction, engineers did something remarkable. They built the entire bridge virtually. Virtual pre-assembly. They mapped out exactly how 93 individual steel truss sections would fit together, a complete practice run before moving a single beam. Each section hundreds of tons. Each placement, millimeter-level precision. Each decision, irreversible. The biggest crane in the world is called Big Carl. It's 250 meters tall, built by a Belgian company. You'd need 3 Big Carls stacked on top of each other just to hover above this canyon. China could probably break that record too, but they used something more elegant instead: a cable crane system. Imagine an overhead cable runway where massive steel sections travel along suspended cables, like a monorail, except instead of rails, it's cables. Workers deliver sections to the canyon edges, lift them upward, and guide them across the void towards their final positions. It's the kind of engineering solution that only emerges when conventional methods fail completely. The sections were placed from the middle outward. This kept the structure balanced throughout assembly, preventing all stress from concentrating on a single tower. Each steel panel was positioned using Beidou navigation satellite system, China's equivalent to GPS. Accuracy down to millimeters, room for error, 0. Here's where most bridges fail: uneven terrain. Unlike flat construction sites, sloped canyon walls distribute structural stress unpredictably. The Hongqi Bridge in neighboring Sichuan province learned this lesson brutally. Dangerous cracks appeared on nearby slopes and roads when the earth shifted. Huajiang's forced Huajiang's engineers into brilliant design innovation. The two support towers aren't identical heights. The northern tower stands 262 meters tall. The southern tower measures 205 meters. This 57-meter difference isn't a mistake, it's the solution. Combined with asymmetrical cable anchorages, this design accommodates the terrain's natural irregularities. Some anchor points were drilled deep into rock, others are shallower. Geology dictates everything. The design follows geology. Guizhou isn't known for catastrophic earthquakes like other Asian regions, but earthquake activity happens here. Any bridge this massive must be ready for that eventuality. Engineers installed shock-absorbing devices at both ends, massive mechanical dampers. When earthquakes strike, these devices absorb and dissipate movement energy while allowing the bridge to flex slightly without snapping. Think of it like a pendulum. When you swing a pendulum and give it a push, it doesn't break, it sways. This bridge does the same. It must move, but it must never fail. If earthquakes present intermittent danger, wind is constant threat. Canyon geography fundamentally alters wind behavior through something called the Venturi effect. Named after physicist Giovanni Battista Venturi, this principle explains why wind accelerates when passing through narrow passages. Pressure drops as speed increases. You experience this between tall city buildings. In canyons with constrained sections, wind becomes turbulent and violent. Local reports indicate gusts reaching speeds comparable to express trains. That wind velocity creates forces that would collapse most structures. Testing happened in specialized wind tunnels. Scale models of the bridge underwent simulated wind conditions showing how the actual structure would respond. But engineers deployed something more advanced: Doppler LiDAR. Most people know the Doppler effect from sirens. Pitch changes as vehicles pass. Engineers use this principle differently. LiDAR is a laser system mapping three-dimensional space by reflecting off particles. Here, scattered laser beams reflect off atmospheric moisture particles. By measuring frequency shifts in reflections, engineers create real-time three-dimensional images of actual wind movement patterns in the canyon. Not theoretical wind, real behavior. This data informed design decisions far beyond what computer models alone could predict. When the bridge opened, engineering responsibility didn't conclude, it began. Those cables support 22,000 tons of steel under constant strain. Engineers couldn't rely on periodic inspections. They embedded fiber optic sensors directly inside the cables themselves. As metal wires expand under load, the fiber optic strands expand identically. Engineers pass light through these fibers, measuring reflections to determine extension, essentially creating real-time strain gauges. Cable tension remains the most critical measurement. Suspension bridges depend entirely on cable integrity. These cables consist of pre-formed parallel wire strands, thousands of individual wires bundled into massive bundles, then bundled again into a single enormous cable. Any change in tension anywhere on the structure triggers alerts monitored 24/7. Workers who move across the structure above use catwalks, elevated pathways requiring extraordinary comfort with heights. Few people possess that kind of fearlessness. Huajiang Bridge cost up to $200 million. Construction took 3.5 years. By most standards, that would merit major international acclaim and accolades. Yet China treats such projects as routine. The nation has more high-speed rail than anywhere else on the planet. Bridge inventory exceeds every other nation's total. Dam construction remains unmatched worldwide. But this initiative transcends mere record-setting. Since 2012, China has invested hundreds of billions into infrastructure development across its poorest regions. This represents deliberate strategy: combat poverty through connectivity. create pathways for economic participation outside major coastal hubs like Beijing and Shanghai. Guizhou specifically participates in the Belt and Road Initiative, a global strategy establishing economic corridors across Asia, Europe, and Africa. China emphasizes how developed these zones have become, positioning them as showcases of national achievement and technological capability. Huajiang Bridge serves dual purposes: practical transportation infrastructure and symbolic demonstration of engineering prowess. It transforms regional economics while projecting global influence. But Huajiang Bridge is far more than a functional crossing. It's designed as a destination. An 800-meter glass elevator ascends one support tower to a two-story coffee shop positioned mid-air above the canyon. Visitors sip beverages while gazing across impossible vistas. In the bridge's underside, glass walkways permit brave souls to gaze downward into the void, 1,000 feet of air beneath their feet. An artificial waterfall cascades down the bridge structure itself, hundreds of meters. China envisions this as an extreme sports destination. A commercial bungee jumping platform allows thrill seekers to leap from the world's highest bridge. Professional base jumping competitions are being planned. A dedicated extreme sports facility is proposed for the canyon below. This represents the contemporary infrastructure vision. Projects function simultaneously as commercial corridors and tourist attractions. Billions of dollars flow into creating transportation networks that accomplish multiple objectives simultaneously: move commerce, attract visitors, generate revenue. Huajiang Bridge exemplifies this convergence perfectly. It connects previously isolated communities to economic opportunity. It demonstrates Chinese engineering capability to the world. It attracts visitors, generating substantial tourism revenue. It stands as a monument to what becomes possible when ambition encounters expertise. Modern engineering doesn't just solve problems, it builds economies. It creates wonders. Huajiang Bridge succeeds on all these dimensions simultaneously. For the Planetary File, this story encapsulates something essential about our world. Our planet's surface continues being reshaped by human determination, innovation, and refusal to accept geographic limitations. Every bridge, dam, tunnel, and highway represents humanity's answer to a challenge nature presented. If you found this exploration of extraordinary engineering as fascinating as we did, hit that like button for the Planetary File. Your support enables us to investigate more incredible feats transforming our world daily. Subscribe to unlock more stories about how humanity engineers solutions to seemingly impossible challenges. Because the most insane structures on Earth have stories worth telling, and the Planetary File is dedicated to revealing them.